Hi, my name is Trent Sacilotto. My ZID is 5344028, and this is my final submission for experiment 1 in understanding the solar system in PHYS1160. So I'm just going to show you my ID. It doesn't have autofocus on the camera at the moment, but should be able to get name, picture there, address. Yeah, we're getting there. There we go. So I'm going to go into the presentation and show the simulations. So I've got the sun-planet orbit running. Now, this relates to Kepler's first law, which states that planets orbit the sun in elliptical orbits with the sun at one focus. Kepler's second law says that a line joining a planet and the sun sweeps out equal areas in equal times, meaning planets move faster when closer to the sun. Kepler's third law relates to orbital period to orbital distance, showing that planets further from the sun take longer to complete an orbit. Jumping to question 9, so the planet-moon system in the center of mass. So when we switch to the planet-moon scenario and we let the moon orbit, now in the planet-moon system, both the planet and the moon orbit around a common center of mass. The planet itself moves slightly as the moon orbits it. In the sun-planet systems, like the Earth and the sun, the center of mass is located very close to the center of the sun because the sun is a much more massive star. In contrast, for a planet-moon system, the center of the mass can lie outside the planet itself. This difference is due to the smaller mass difference between the planet and the moon. Going on to question 11. Now we've got to switch it to the scale and the grid on with the Sun-Earth system visible. So into the scale mode, the grid spacing represents astronomical units. Each grid marking corresponds to 1 AU, astronomical unit, which is the average distance between the Earth and the Sun. This shows how large and spread out the solar system really is and helps demonstrate realistic spatial distances between planets. As we go on to question 14, now we've got some clear circular orbits at different distances. These are as per what's been shown on the screen at the moment. As the orbital distance increases, the time taken for the planet to complete one orbit also increases. These results follow Kepler's third law, which shows that planets further from the sun have longer orbital periods. These results follow Kepler's third law. Now we've got, for question 15 and 16, for the fastest and slowest orbital speeds, is that the fastest orbital speeds occur for planets closest to the sun, such as Mercury, while the slowest speeds occur for planets further away, like Neptune. Now, this happens because gravitational force is stronger at smaller distances, causing planets to move faster when closer to the sun. Overall, this experiment helps me understand how planetary orbits in the solar system are mainly controlled by gravity, distance, and velocity. I've learned that stable Earth-like orbits occur when planet's velocity is set correctly relative to the gravitational pull of the star. Now, one important result was the changing mass of the planet did not significantly affect the orbit when the star was much more massive. Even though the gravitational force increased, the acceleration stayed similar, showing that orbital motion is dominated by the star's mass. Now, changing the planet's velocity had a much larger effect. Reducing velocity caused the orbit to become more elliptical. The planet also moved faster when it was closer to the star and slower when it moved further away, which demonstrated Kepler's second law. I've learned that both objects in a system experience equal and opposite gravitational forces and orbit a common center of mass. This was especially clear with the Sun-planet system to planet-moon systems. Finally, the experiments showed that planets further from the star take longer to orbit, which follows Kepler's third law. Overall, the simulation helped me clearly connect Newton's law and Kepler's law to real planetary motion in the solar system.